Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 33rd lecture on sampling-based motion planning. All right, so let's get started with a video. Now, this is a video of two autonomous robot arms that are performing manipulation tasks. These tasks involve motion planning. Each arm has a start position, and the robot has to plan how to move from that start to the object, and then plan how to move that object to the goal. I like this video because it's so dynamic. The human keeps giving the robots new tasks to complete and moving things around in the environment. And so the robots have to think on the fly and modify their motion plan in real time based on the environment and the human. In today's lecture, we'll be discussing motion planning. First, I want to talk about how we can make motion planners that are efficient and complete, especially for serial robot arms. And then second, I want to introduce rapidly exploring random trees, or RRT. Okay, so let's set the stage with motion planning. The big idea with motion planning is I want to find a trajectory that moves my robot from the start to the goal and avoids any obstacles. You can see an example over here on the left. I've got my robot arm, I've got a start position, I've got a goal that I know I want to reach, and I use motion planning to come up with a sequence of waypoints that goes from the start to the goal and avoids this obstacle. Once I have that plan, I can then use a controller to actually execute it in the real world. So I'll use a controller to guide my robot to each of these different desired positions and actually physically move that system to perform this task. In our last lecture, we talked about one motion planning approach called trajectory optimization. As the name suggests, this is an optimization-based approach where we give the robot a loss function, and it tries to find a trajectory that will minimize that loss function. Here, the loss is the overall distance or length of the trajectory, as well as making sure I avoid obstacles. And so the drone comes up with a plan that goes from the start to the goal, and it smoothly moves along the edge of this obstacle. Trajectory optimization was great. It had many strengths, but it also has some weaknesses. And one of the challenges is because it's an optimization-based approach, it can get stuck in local minima. Here's an example. My robot thinks it's found a valid solution, but actually it's colliding directly with this obstacle. So the motivation for today's lecture is how do we solve this problem? How do I come up with a complete planner that will find a solution if it exists and won't get stuck in these local minima? It's actually not a very easy question to answer. And the first step towards answering this question is maybe framing motion planning as a search problem. So to avoid local minima, maybe what we could do is I could decompose the environment into a grid, and then I could search that grid for the best trajectory that avoids obstacles. Let me show you what I mean with this example on the right. I've got a start position and a goal position, and then some obstacle I know I want to avoid. With this approach, what I do is I would take this space and I would divide it up into these different cells of a grid, and then I would search those cells for the shortest feasible path. I could use something like A-star algorithm or Dijkstra's algorithm. And it is feasible in some situations to do this. Like here, I find a path from the start to the goal. But there are some very key fundamental issues with this approach. So maybe you want to pause the video and think for yourself, what are some of the challenges if you want to go with this sort of brute force search? I noticed two issues, and they both stem from the size of these cells. If you make the cells too big, you're going to miss out on solutions. Like right here, my robot thinks it can't move through this cell because there's an obstacle in it. But if the cell was smaller, my robot could realize, oh, okay, I can just move around the obstacle and go directly to the goal, and this is a much more efficient path. So that's if the cells are too big. On the other hand, if you make the cells too small, the search space increases in size. And this quickly becomes sort of impossible for my different algorithms to solve. So let's say you've got a 7 degree of freedom robot arm. And let's say I discretize each joint with a resolution of 100. And what that means is I'm thinking about increments between 0 and 360 degrees, and I've got 100 of those increments. I don't think this is a crazy level of resolution, but it makes the entire search problem infeasible. Because now I've got to search through 100 trillion nodes, and that's going to be intractable for any of these algorithms. So brute force search isn't really going to work. And that means I have to come up with another approach. Again, I'm trying to find something that's complete, that will find a motion plan if one exists, and isn't going to get stuck in these local minima. At the same time, I want to make sure I'm efficient and I can scale up to these robot arms with multiple different joints. So one solution to this is the RRT algorithm. And what I want to do is in today's lecture, I want to give you the kind of the high level intuition and these steps behind this algorithm. Then in the next lecture, I'm going to give you more detail on the actual implementation for this approach. So again, today we'll be focusing on the steps and the intuition for RRT. The core idea is that instead of decomposing the entire space and performing a brute force search across all those different cells, we're going to sample positions at random. We're then going to check for each of these positions that we sample, is that a valid position? Like, is there a collision there, or is that something that we actually could reach? Then, if that position is valid, like there is no collision, can we connect that new position to other collision-free positions that we've seen before? And then as we keep connecting all of these different collision-free positions, can we extract some sort of trajectory that goes from the start to the goal? These are some of the basic ideas, and let me show you what that means more in terms of the algorithm. So on the left, I'm going to have the algorithm, and we're going to build this up step by step. On the right, I'm going to try to visualize these steps with an example. So I've got my start position, I've got my goal. And the way this algorithm is going to work is it's going to build something called a graph. We're going to call that graph G. Now, this is just a data structure that's going to contain and connect our collision-free positions. So you can kind of think of this as our memory of all the different positions we found so far that are valid, that are collision-free. So at the beginning, my graph is just going to contain my start position because we know this is a valid position that I could start with. And then I'm going to try to build out that graph with every time I go through this while loop. The first step I do is I just sample a random joint position. And when I say random, I mean random. Like you look at all the feasible joint positions your robot could have and pick one of those uniformly at random. Here I've got theta rand. The next thing I'm going to do is I'm going to look and figure out in my graph what node or what point in that graph is closest to theta rand. In this case, it's pretty simple. I only have one point in my graph, that's theta near. So great, I'll call that the nearest node and I'll rename it as theta near. All right, then I'm going to take a step from theta near towards theta rand, and that'll propose a new position called theta new. So it's kind of a two-step process, but really all we're doing right here is we're just sampling random positions, and theta new is this kind of new random position that we're sampling. And I want to check and see, is this new position valid? Like, can I add that to my graph? And so that's going to be the next step of my process. I check and see, is theta new collision free? If it is, like it is in this example, then I can connect it to my graph. So I make a connection between theta new and theta near. And so now those two things are my graph, and I also understand that I can move from between these two different points. All right, so that's the first time I go through this while loop. Let's go through the while loop again. So again, I'm going to uniformly sample something completely at random. I'll sample this joint position. And then I'm going to look in my graph and see what node is closest to that random joint position. In that case, it's going to be this one right here. I'll call that theta near, and I'll move towards theta rand, and that's going to generate theta new. Again, it's like a two-step process of finding these random joint positions, and I want to just test and see, are they feasible? Here, I'll again check and see, is there a collision for theta new? There isn't, so I can add it to my graph. And so now I've got this updated graph, and I'm just going to keep doing this of sampling random joint positions uniformly at random from my joint space and see if I can add them to my graph. Now, there'll be times when I can't, like what you see right here. I've sampled a random position. I found the nearest node in my graph. It's this one right here. I move towards that randomly sampled joint position. I call that theta new. And this one isn't going to work. It's in collision with the obstacle. And so all I do is I just skip it over and I try again. So I won't include that in my graph. And I'm going to restart this and sample another random joint position. As I keep doing this and building out my going through this while loop, I'm going to build out a larger and larger graph with all these different feasible joint positions. And I like this for two reasons. First off, it's telling me about all these different joint positions that are not in collision. These are all feasible. And it's also telling me about how they connect. Like I understand that I can move from theta start either to theta 1 or to theta 4, and there isn't a collision there. So I'm kind of building out this graph of all these different feasible nodes and the way I can move between these nodes. Eventually, I'm going to stop this process when I find a node that is close to my goal. So I'm going to set some radius epsilon. I'm going to say that, all right, whenever you find something that's close enough, we'll just say we've got there, that's good enough, and we'll stop our search there. So if I find that, I'm going to say success. I have found a valid motion plan from the start to the goal that avoids obstacles. And if I go through this budget of n different times and I never find a valid path, I'll just give up and say failure. We call this probabilistically complete because it's not technically complete, but as n goes towards infinity, If there is a valid path, you will find it. And if there is not a valid path, you will say, I return failure. So it's not totally complete, but it's almost there. All right, let me show you what this process looks like with a video. Now, I'll explain the video and we'll talk a little bit about what it means. Here's my start position. So I'm going to start off at 0, 0. And then here's my goal. I want to go to 1, 1. I'm just in an XY grid, XY plane, and where the Z-axis is coming out of the screen towards you. And then I've got this obstacle right here that I want to avoid. So I know I want to avoid this obstacle. Okay, now let's watch this again. So the robot is sampling these random joint positions and checking to see, are they feasible? If they are, it's adding them. And eventually it's kind of building out this graph. And you can see how this graph is moving out uniformly. It's covering all the different areas of the space. And eventually this graph finds a joint position that's within my radius of my goal. And I now have a valid trajectory that goes from the start to the goal and avoids my obstacle. You might want to consider the differences between this and trajectory optimization. Both of them can find paths from the start to the goal. This will be robust to local minima, but as you can see, the path we find isn't necessarily the smoothest path for my robot to follow. We're going to keep talking about that in our next lecture, but I want to pause here, and I encourage you to go through the practice set. You can find that in the discussion or the pinned comments. The first page has the questions and the following pages have the answers, and you can use this practice set to deepen your understanding of the RRT algorithm. Overall, in today's lecture, we've talked about what motion planning needs in order to become complete and efficient. And we discovered that one way to do that is using the rapidly exploring random trees, or RRT. In the next lecture, I want to continue along this theme by giving more details about the RRT algorithm and showing you how you can implement this in practice. So I look forward to seeing you there.